A quantum dot display is an experimental type of display technology. Quantum dots or semiconductor nanocrystals could provide an alternative for commercial applications such as display technology. This display technology would be similar to organic light-emitting diode displays, in that light would be supplied on demand, which would enable more efficient displays. Quantum dots could support large, flexible displays but would not degrade as readily as OLEDs, theoretically making them good candidates for flat-panel TV screens, digital cameras, mobile phones and personal gaming equipment. At present, they are used only to filter light from LEDs to backlight LCDs, rather than as actual displays. Properties and performance are determined by the size and/or composition of the QD. QDs are both photoactive and electroactive, allowing them to be readily incorporated into new emissive display architectures. History. The idea of using quantum dot as a light source emerged in the 1990s. Early applications included imaging using QD infrared photodetectors, light-emitting diodes and single-color light-emitting devices. Starting from early 2000, scientists started to realize the potential of developing quantum dot for light sources and displays. A widespread practical application is emerging in so-called quantum dot TVs. It must be noted, however, that these new TV sets are still LCD TVs as far as picture generation is concerned. QDs are used to improve the backlighting. In addition to using LEDs for backlighting, light from a blue LED is converted by QDs to relatively pure red and green, so that this combination of blue, green and red light incurs less absorption of unwanted colors by the color filters behind the LCD screen, thereby increasing useful light throughput and providing a better color gamut. The first TV manufacturer shipping TVs of this kind was Sony in 2013, although not yet labeled as a QD TV. At the Consumer Electronics Show 2015, Samsung Electronics, LG Electronics, the Chinese TCL Corporation and Sony showed QD-enhanced LED backlighting of LCD TVs. Working principle. Optical properties of quantum dots. Unlike simple atomic structures, a quantum dot structure has the unusual property that energy levels are strongly dependent on the structure's size. For example, CDSE quantum dot light emission can be tuned from red to the violet region. The physical reason for QD coloration is the quantum confinement effect and is directly related to their energy levels. The band gap energy that determines the energy of the fluorescent light is inversely proportional to the square of the size of quantum dot. Larger QDs have more energy levels that are more closely spaced, allowing the QD to absorb photons of lower energy. In other words, the emitted photon energy increases as the dot size decreases, because greater energy is required to confine the semiconductor excitation to a smaller volume. Quantum dot light-emitting diodes. Quantum dot-based LEDs are characterized by pure and saturated emission colors with narrow bandwidth. Their emission wavelength is easily tuned by changing the size of the quantum dots. Moreover, QD LED offer high color purity and durability combined with the efficiency, flexibility, and low processing cost of organic light-emitting devices. QD LED structure can be tuned over the entire visible wavelength range from 460 nanometers to 650 nanometers. The structure of QD LED is similar to the basic design of OLED. The major difference is that the light-emitting centers are cadmium selenide nanocrystals. A layer of cadmium-selenium quantum dots is sandwiched between layers of electron-transporting and hole-transporting organic materials. An applied electric field causes electrons and holes to move into the quantum dot layer, where they are captured in the quantum dot and recombine, emitting photons. The spectrum of photon emission is narrow, characterized by its full width at half the maximum value. The challenge of bringing electrons and holes together in small regions for efficient recombination to emit photons without escaping or dissipating, was addressed by sandwiching a thin emissive layer between a hole transporter layer and an electron transport layer. By making an emissive layer in a single layer of quantum dots, electrons and holes may be transferred directly from the surfaces of the ETL and HTL, providing high recombination efficiency. Both ETL and HTL consist of organic materials. Most organic electroluminescent materials favor injection and transport of holes rather than electrons. Thus, the electron-hole recombination generally occurs near the cathode, which could lead to the quenching of the excitant produced. In order to prevent the produced excitants or holes from approaching the cathode, a hole blocking layer plays dual roles in blocking holes moving towards the cathode and transporting the electrons to the emitting QD layer. Tris aluminium, bathoxypron, and TAS are the most commonly used hole blocking materials. These materials can be used as both electron transporting layer and hole blocking layer. The array of quantum dots is manufactured by self-assembly in a process known as spin casting. A solution of quantum dots in an organic material is poured onto a substrate, which is then set spinning to spread the solution evenly. Fabrication process. Quantum dots are solution processable and suitable for wet processing techniques. The two major fabrication techniques for QD-LED are called phase separation and contact printing. Phase separation is suitable for forming large area ordered QD monolayers. A single QD layer is formed by spin casting a mixed solution of QD and TPD. This process simultaneously yields QD monolayers self-assembled into hexagonally close-packed arrays and places this monolayer on top of a co-deposited contact. During solvent drying, the QDs phase separate from the organic underlayer material and rise towards the film's surface. The resulting QD structure is affected by many parameters: solution concentration, solvent ration, QD size distribution and QD aspect ratio. Also important is QD solution and organic solvent purity. Although phase separation is relatively simple, it is not suitable for display device applications. Since spin casting does not allow lateral patterning of different sized QDs, phase separation cannot create a multicolor QD LED. Moreover, it is not ideal to have an organic underlayer material for a QD LED. An organic underlayer must be homogeneous, a constraint which limits the number of applicable device designs. Contact printing. The contact printing process for forming QD thin films is a solvent-free method, which is simple and cost-efficient with high throughput. During the process, the device structure is not exposed to solvents. Since charge transport layers in QD LED structures are solvent-sensitive organic thin films, avoiding solvent during the process is a major benefit. This method can produce RGB patterned electroluminescent structures with 1000 pixels per inch resolution. The overall process of contact printing. Polydimethylsiloxane is molded using a silicon master. Top side of resulting PDMS stamp is coated with a thin film of parylene C, a chemical vapor-deposited aromatic organic polymer. Parylene C-coated stamp is inked via spin casting of a solution of colloidal QD suspended in an organic solvent. After the solvent evaporates, the formed QD monolayer is transferred to the substrate by contact printing. Contact printing allows fabrication of multicolor QD LEDs. A QD LED was fabricated with an emissive layer consisting of 25 µm wide stripes of red, green and blue QD monolayers. Contact printing methods also minimize the amount of QD required, reducing costs. The demonstrated color gamut from QD LEDs exceeds the performance of both LCD and OLED display technologies. Comparison. Nanocrystal displays would render as much as a 30% increase in the visible spectrum, while using 30 to 50% less power than LCDs. in large part because nanocrystal displays wouldn't need backlighting. QD LEDs are 50 to 100 times brighter than Corten LCD displays, emitting 40,000 candelas per square meter. QDs are soluble in both aqueous and non-aqueous solvents, which provides for printable and flexible displays of all sizes, including large area TVs. QDs can be inorganic, offering the potential for improved lifetimes compared to OLED. Other advantages include better saturated green colors, manufacturability on polymers, thinner display, and the use of the same material to generate different colors. However, blue quantum dots require highly precise timing control during the reaction, because blue quantum dots are just slightly above the minimum size. Since sunlight contains roughly equal luminosities of red, green and blue, a display needs to produce approximately equal luminosities of blue, red and green. The human eye requires blue to be about 5 times more luminous than green, requiring 5 times more power.